Swayam Prabha. Digital India. Educated India.
Well, still staying with probability. So, let's say this is part 2. Like you have sequel to movies, we have sequel to what we did yesterday. Right. So, we saw, we learned what were random variables, we talked a little bit about expectations, linearity of expectations. Now, what is our goal here? Now, see, I mean, when you study probability there, it's like, well, you might say that this is a mathematically a nice subject and all that, but we study this for, applying it to computer science. So, there must be reasons when, or areas where we use probability. Now, today's lecture is themed around the following fact. Let us say, for example, I have a random variable x. So, it would be following a distribution. So, you know distributions, right? Normal, binomial, Poisson, geometric, hypergeometric, negative binomial, there are distributions galore, many of them. Now, why do you kind of develop distributions? The reason being that if you look into real life applications and model it where there is some amount of randomness involved, you see that it follows certain patterns and that brings you to distributions. Now, the moment you get a random variable which follows a particular distribution, we say that we know how this random variable behaves. What do I mean by that? That I can talk of its expectation, I can talk of its variance. Now, expectation is we know this definition, right? Now, I might tell you that I want to know this. So, this is known as the second moment of this random variable. So, similarly, you might want to know what is the nth moment of this distribution of this random variable. Right? Now, say for example, you have, as Venkatesh would talk of randomized algorithms next, you would see that there are random processes which you cannot straight away fit into any one of these known distributions. Then what do? Can you say anything good about these random variables? So, what computer scientists mostly do is, others also do, say I look at the random variable x and see look at its values away from the expectation. I would say that this random variable is kind of well distributed if this takes values close to its expectation. Then just finding its expectation suffices, right? Like say for example, Venkatesh would talk of quicksort in the next lecture, and you do an expected case analysis of n log n for quicksort. but you know that in the worst case quicksort may run up to n square. So, you know there are instances even if you randomly pick the pivot where quicksort would take time more than n log n, but on the expectation it is n log n, right. Now, if it is so and if I can mathematically prove, now first figure this out, that the moment you take a random variable, say for example he picks a pivot uniformly at random. Now, the time that you would have for your algorithm would now become a random variable, because it is the outcome of a random process, because you are choosing your pivot randomly. So, whatever your pivot you might choose, your time would depend on that. So, if you are choosing a pivot that is kind of centrally located, you would get kind of balanced partitions, and then you have this nice recurrence which kind of does a nice divide and conquer, and you would get n log n. But there may be instances where you are not picking up a good central splitter. The pivot that you pick is kind of towards the margins, and then you will have unbalanced partitions. You tend to have results close to quadratic n square. So, that means your random variable is going to take values in a range, and I would be very happy if I can predict or can kind of mathematically prove that the random variable is taking values very close to its expectation. So, what do I do for that? For that, I look into this probability. By now you know this is going to make sense, right. So, I look at all those values of the random variable that is away from its expectation, and then I would say, well, by how much, and then I would try to probably put a bound that this probability is not very high. So, that means x is not going to take a value away from the expectation too much. So, probability, if I can bound that probability, then I am sure that the random variable x is very close to its expectation. So, this is actually the philosophy of tail inequalities. So, when we do tail inequalities, we want to basically comment on these kinds of probabilities, that how, so that is why it is known as the tail, it is how far the random variable is going away from its expectation, right. So, this is the intuition of what we would be doing today. So, now I would kind of start getting a little bit formal. Maybe I can just say one thing, and that it's like without any proof, that if you know all the moments of a distribution, so variance is actually a second moment. There is a correction term, but variance is actually a second moment. I will come to the definition of variance shortly. But if you know all the moments of a random variable, you can explicitly say about its distribution. So, knowing the moments of a random variable is of utmost importance. So, till now we have seen the first moment, which was the expectation. We are going to see more moments. So, the next in line is variance. So, let us start by, again I would not prove all of the results, rather push some of them to the tutorial. Okay. So, let us start by defining variance, because this would be useful for our tail inequality. So, what is this? Second moment, and you take this, right. So, you look at the random variables, how far it is from its expectation, take the square of it, take its expectation. Now, if you do a few steps, if you simplify this expression, this would come to if you just open up this square, apply linearity of expectation, you will end up here, right. So, do this as an exercise. Okay. So, like in expectations, we defined expectations and then looked at sum of random variables and took its expectation. Linearity of expectation was working fine. So, obviously, we would pose the next question in here, that what if I have two random variables not necessarily independent and I want to figure out the variance of this. Well, how do you do it? You fall back to the definition. So, it is like expectation of x plus y minus x plus y whole square, take its expectation and then deduce out things. Now, when you look at two variables, it's not, if it's not independent, it's like you cannot just sum variances as you did in the case of expectation. Okay. So, there is a term called covariance. So, do you know this term covariance? Anyone? Covariance? How two variables are going to, huh? Okay. Let us see. So, before I get into how we do this, I mean basically what we want to do is we want to deduce we want to figure out what is this. Like we did in the case of linearity of expectations, we want to do this. What happened? So, before going into actually deducing those expressions, let us look at what is covariance. So, for two random variables x and y, covariance is defined as this is also an expectation of so you take the expectation of this product. Right. So, look at the random variable x, see how far it is from its own expectation, take the product with the other random variable and how far it is from its expectation. Now, what you would see is, if you now, for want of time I would not formally do it. So, if you now look into this variance of x plus y, so plug in x plus y in the place of x there, and so you now have an expression like expectation of x plus y minus expectation of x plus y whole square. So, on expectation of x plus y you can apply linearity of expectation, right. So, this way do this deduction. If you complete that, what you would get is will have a covariance term. Again, this is an exercise. So, because you understand that if you open up that term, there would be a product term, right, in terms of x and y. And again you apply linearity of expectation because there is an expectation outside. So, you would get a term like expectation of x minus expectation of x into into y minus expectation of y. So, do this yourself. We will probably help you in doing this during the tutorial. Now, the general result is again exercise will help you out with this in the tutorial. So, as I want to go a little fast, I am not going into these reductions. So, Uddalok and me would be there in the afternoon to help you out with these things. Well, so the take home message in here is when you look at the variance of a sum of collection of random variables, not necessarily independent, then you individually sum the variances and look at a covariance term, which is basically the expectation of the product of these random variables away from their expectation. Fine. Now, what if, like, so when we are seeing linearity of expectations, we saw that how these random variables behave among themselves, whether they are independent or not, had no bearing on linearity of expectations, but that is not the case with variance. So, for that let us look at the following thing. Are two independent random variables. Now, see, I mean, it's like I'm going a little bit fast in here. I had yesterday defined to you what was independence of events, right. So, likewise you can also define what is the independence of random variables, right. So, random variables taking certain values, from there you can form events, and then that definition of independence of events follows. Okay. So, what should be covariance of x y? 0. Why? You know the definition, right? Just go ahead and expand it quick. So, your definition is expectation of x minus ex into y minus expand it. you can expand it, but you can also look at the following. Am I correct if I write this? Yes, no, maybe? When the instructor has written, it should be correct, no? Again, as I was telling you that I was going very fast, fine. You remember last day we did this, that if you have two random variables that are independent, then expectation of their product is equal to the product of their individual expectations. So, expectation of x into y was equals to expectation of x into expectation of y. But this is now no longer x, this is now a function of x, right. What kind of a function? A good linear function, x minus ex. So, expectation of x is kind of constant with respect to x, right. Now, again one can prove this, that if two random variables are independent, then fx, say you have two random variables x, y, then if you look at fx, some function over this random variable x, and you look at gy, which is a function on the random variable y, then these two new functions fx and gy, they are also random variables and they are also independent, right. One can prove this. Again, I am not going into the proof. So, I use that result. So, x minus ex is a function of x. Similarly, y minus expectation y is a function of y. So, I am looking at x and y were two random variables. In here, I am looking at expectation of fx into gy. They are also independent because x and y are independent. And if x and gy are now two new independent random variables, the same theory applies of yesterday's. I can write them as product of their individual expectations, right. Again, as I say, all of this what I am saying needs a proof, but due to paucity of time I am not going into the exact proofs. So, until and unless one can prove that functions of random variables are also independent, I could not have written this. Now, once I can write this, now you can easily understand that expectation of x minus ex is what? 0, right, because again linearity of expectation applies. So, if you open it, it is expectation of x minus expectation of x, which is expectation of x, right. So, this turns out to 0. So, this is equals to 0. So, if you have two random variables which are independent, then their covariance is equals to 0, and if their covariance is 0, then individual variances just add up because the covariance term is 0. So, you can now write a new theorem. So, for a finite collection of independent random variables x1, x2 up to xn, variance of their sum is nothing but their sum of their individual variances, right, because this covariance term gets to 0. Fine. So, I would just kind of so are you people conversant with this binomial distribution, Poisson distribution, normal distribution? Are you people familiar with this kind of things? Now the tragedy is, you know these distributions, but you don't know almost anything about random variables, right. So you need this bridge to know about random variables and then come to know what kind of distributions those random variables follow, right. So when you analyze any algorithmic process or any kind of process in computer science which is random in nature, you model it using a random variable. If this random variable fits into a known distribution, nothing like it, it is very good, you are done, because for a known distribution you know all its moments, so everything is known. But life would not be that simple. The random variables or the random processes that you would get would not kind of fit into these known distributions. Then you have to, the process starts. Then you have to know, as I said, the more you know about the moments of the random variables, you know which kind of or what kind of distribution this random variable follows. So you would want to know more about these moments. Now the moment you start knowing more about these moments, whether the random variables are independent or not becomes very important, because if they are not independent, then there is this covariance term. Handling this covariance term is not going to be that easy. So then individual variances would not add up, same for higher moments, right. So this is the way this theory is developed, and as I said earlier, I would now slowly get into talking in terms of how this random variable is distributed away from its expectation. And how can I say it? I would say it in terms of a probability measure, and by now you know that probability is over sets. So when I write x minus ex, this is now a very clear thing, it should be a very clear thing in your heads, right. Any questions till now? Fine. So let me just do one distribution which I kind of started with, yeah, geometric random variables. You remember the first experiment, that first example that we discussed was about what? Coin tossing, that success probability P, on the expectation you require 1 by P. Fine. So what is the probability distribution? So there is a problem with this pen, this eraser is so close to this, sometimes you press it while you write, and then writing and erasing kind of becomes simultaneous. Okay. To fix the distribution for a geometric random variable, you need only one thing, you need one parameter, which is the success probability P. Okay. So what you are doing? You are doing coin tosses one after the other, and any one of your tosses does not depend on the outcome of any the outcome at the ith step does not depend on any one of the previous steps. Okay. So I look at the probability that x takes the value I. So that means you get the success at the ith step. So that means you have got failures before that, and then you get a success. Okay. So first exercise, what is a PMF? Do you know? Probability mass function. So when I write show that it is a PMF, what does it mean? That if you sum these probabilities over all i's, you should get equal to 1, right? Fine. Okay. So that is the bound waiting for the first success. I want to figure out the expectation of the amount of weight, by that I mean the amount of experiments I did to get the first success. Right? Just the basic definition of expectation. Now you plug in the values. So instead of 0, I can start the index of the sum from 1, right? Because if you plug in 0, it is like meaningless. So I would kind of write this as 1. Now you would actually get an arithmetical geometric sum out of it, do a few steps, and this would give you 1 by p. So exercise. So p does not depend on I, so bring out p and then bring out 1 minus p out of it. So you would get a term like I minus 1 into 1 minus p to the power of I minus 1. Just do an arithmetical geometric sum. Fine. So this is the desired result of yesterday. So after having known variance, we are now in a position to get into tail inequalities. So as an exercise, what you can do is you look at Poisson, you look at binomial, and you can figure out what is the PMF, what is the expectation, so on and so forth. Okay. Like say for example, if you look at say binomial. So for binomial, how many parameters do you need? 2, n and p, the number of times you do the experiment and the probability of success, right. So it is like n choose r, 1 minus p to the power of r, p to the power of n minus r, so on and so forth. Now see, for a binomial, you are doing repeated n experiments, right. Each one of these experiments is a success failure thing, and it happens with the same probability p, right. So you can now see a binomial random variable as the sum of such 0, 1 success probability kind of random variables. So each one of this, where you do one experiment, it is either a success or a failure, is known as a Bernoulli trial, right. And if successive repetitions of this has the same probability of success p, this is called Bernoulli trials. If the success probability varies, it is called a Poisson trial. We will look into Poisson trial later on. But for binomial trials, it is the same experiment 0, 1 or success failure with the same probability p. Now for binomial, you can see it as a sum of Bernoullis, each one with a probability p. Yesterday we did this, that for 0, 1 random variables, expectation is nothing but the sum of x equals to 1, right? Sorry, not the sum. Right? For a 0 1 random variable, the expectation is nothing but the probability that this random variable takes the value 1. So, for each one of these Bernoullis, what is the expectation? It is p, right? A binomial is now a sum of such random variables. How many? N. Linearity of expectation applies. Now see, you can very easily, without doing those complicated combinatorial expressions, you can figure out that the expectation of a binomial is nothing but n into p. But you just go back and recall when you encountered binomial first and you tried to figure out the expectation of a binomial random variable, you did a a messy kind of algebraic combinatorial stuff, right? N choose r, you summed it over r, and then kind of you handled a very messy expression. But the moment you bring in linearity of expectations, you see how easily you can deduce these expressions. Anyway, so let us now get into tail inequalities. Professor, I have time till 11, no? 11, fine. So, the first tail inequality that we would do is known as Markov's inequality. So, we have on our agenda to do 3 tail inequalities. One is Markov, the other is Chebyshev, the other is Chernoff. Now, both Chebyshev and Chernoff are kind of, what should I say, it is like nice and advanced applications of Markov, but at the heart of it, both Chebyshev and Chernoff are essentially Markov inequality, right. So, let us look into the setting of Markov's inequality. So, we are in a situation that for a random variable, say for example, we do not know anything beyond the expectation, right. See, the moment second moment comes, you are looking at a product of random variables, and by now you know that if these random variables are not independent, handling products is not easy, fine. So, we are in a situation where just we know the expectation. Now, can we make certain comments about how far x, the random variable, is away from a particular value a? Now, Markov's inequality has certain restrictions on the random variable and these values a. So, x is a random variable that is going to take only positive values, it can take 0, so non-negative value. Okay. So, when I write this, does this make sense to you? X greater than a, right. So, look at all x's, all values of the random variable which are greater than equal to a, where a is a positive number. Then this is upper bounded by